Okay, this is an acids and bases question. It's a year 13 topic. Quite a lot of calculation in here. It goes from A through to F. So try the whole question and then review when you're done. Here's A and B. C and D. And E and F. Okay, so let's start to review the answer. The first one is a straightforward definition. You have got to know that strong acids will fully dissociate in solution. On to B. In an experiment, we have got a volume and concentration of HCl and a volume and concentration of barium hydroxide. We're going to add those together and we need to know the pH of the resulting solution. 6-mark question, so a lot of steps in this calculation. And remember, always go back to check how many decimal places you need in your final answer. In this case, it's very clearly 2. So I can colour coordinate here so we can see where the numbers have come from, but that allows me to work out how many moles of HCl we began with and how many moles of barium hydroxide we began with. But we've also got to remember that in this reaction we're interested in the H plus reacting with the OH minuses. It's neutralisation. Now 1 mole of HCl will yield 1 mole of H plus, but 1 mole of barium hydroxide will yield 2 moles of hydroxide ions. And for that reason, we need to work out the moles of H plus and OH minus, as I've done here. I've got 1.035 by 10 to the minus 3 moles of H plus. I've got 7.5 by 10 to the minus 3 moles of OH minus. So the OH minus is definitely in excess. We need to know how much it's in excess by. So I subtract my moles of H plus from it because they will all be neutralised, and I'm left with 6.465 by 10 to the minus 3 moles of OH minus. Now from there, I need to know the concentration of OH minus. So I use N over V. I've got my moles I've just calculated, and I divide by the volume. 35.35 cm cubed. That's because I started with 25 of the barium hydroxide and a further 10.35 of the hydrochloric acid. So I have a total volume of 35.35, and of course I'm dividing it by 1,000 because I need it to be in decimeters cubed. Once I've done that and I have my concentration, I can use this along with the Kw value that I was provided with to work out the concentration of H plus ions. So my expression for Kw is here. I rearrange it to make H plus the subject. I put my figures in and I end up with an H plus concentration of 8.0378 by 10 to the minus 14. I can now substitute that in to my pH expression, giving me a pH to 2 decimal places of 13.09. And I'm putting up here all of the mark allocations so you can see which ones you would have picked up. Okay, moving on to part C, why the water is neutral at this temperature. It's really important that you remember the pH of pure water is only 7.00 at 298 K. So when it changes, the pH value changes. But when you're dissociating water, every water molecule that dissociates gives you 1 H plus and 1 OH minus. So that means the concentration of them are equal to each other. That's why it's neutral. In terms of D, which oxide could react with water to form a solution with pH 2? Well, pH 2 is acidic. Acidic oxides are non-metal oxides, which dismisses aluminium and sodium oxide. And silicon dioxide, sand, does not dissolve in water. So we're not going to get, certainly a strong acid, you're not going to get an acid at all there really. But it leaves us with SO2, and it shouldn't be a surprise that SO2 will give us a solution with pH 2 because it's one of the major contributing factors in terms of the production of acid rain. Moving on to E and F, well Ka, just like Kc, is the product over reactants. It's concentrations, so we use square brackets, and we put those in here. And when it comes to the calculation below, a buffer calculation, 5 more marks to be had here. I can calculate my moles of HCl that I'm adding to my buffer. Now within my buffer, I've also got a reservoir of ethanoate ions and ethanoic acid. I can calculate how many moles of ethanoic acid I started with because I've got a concentration and a volume. I've also been told that I've got 0.025 moles of sodium ethanoate. Now that means, because we know the salt fully dissociates, I've got 0.025 moles of ethanoate ions. From there, my ethanoate ions, my 0.025, will decrease by 0.01 because 0.01 moles of H plus ions have combined with them. So we're left with 0.015 moles. I know that I started with 0.035 moles of ethanoic acid, and I know that that's going to go up by 0.01 because those ethanoate ions that have gained H pluses have become CH3COOH. So I've now got my molar quantities after the addition of a small volume of acid. Now, if I rearrange my dissociation, acid dissociation expression, I can make H plus the subject. And it comes to Ka times CH3COOH over CH3COO minus. Bear in mind these are concentrations, not number of moles. But if I put the volumes in, I could work out the volume and put it in, but actually they're going to cancel out. 1 over V over 1 over V. Once I have done that, I can calculate my concentration. It comes to 5.28 by 10 to the minus 5, and I can substitute that in to my pH expression, giving me a pH of 4.28.